My name is Mr. Isasi, and today I'll be presenting writing exponential equation into logarithmic form and vice versa. Okay, but here are the topics that I'm going to cover today. Exponential properties, converting radical expressions to exponential expressions and vice versa, simplifying radicals, exponential functions, graphs, writing exponential equations into logarithmic equations and vice versa, logarithmic functions, and application problems. This workshop will assist students taking the 0324 for the first part and also for the 1324, which is the second part. Okay, let's begin by exponent properties. There are certain properties that students must know, in order to be successful in this course. Okay, here's here's some of the properties. If m and n and p are integers and a and b are real numbers, then rule number 1 applies, which is called the product rule. For example, the a is called the same base. Okay, the a's are the base and the m is the exponent. So if you have the same base, then you can apply the rule, which means when you have a to the m times a to the n, you have the exponents. Rule number 2 is called the quotient rule. Here, the quotient rule, if you have a to the m over a to the n, right, when it's division, you subtract the exponents. And a cannot be 0 because it will be undefined. Rule number 3 is called the power rule. When you have a base raised to a power raised to another power, you multiply the powers. For example, a to the m to the nth power will be a to the m times n. This is called the power of product rule. For example, if you have a times b to the n, then you distribute the exponent. So it's going to be a to the n times b to the n. Furthermore, if you have a to the m times b to the n, right, to the p power, it's going to be a to the m times p times b to the n times p. Right now, I will show you examples of all these rules. Rule number 5, the power of quotient rule. If you have a to the a divided by b to the n power, then it's going to be a to the n times b to the n. And b cannot be 0 because if the denominator is 0, it's undefined. And furthermore, if you have a to the m over b to the n to the p power, it's going to be a to the m times p over b to the n times p. This is called the negative exponent rule. If you have a to a negative exponent, you make it positive by taking the reciprocal or just put it 1 and then just put it, and then it becomes positive. It's going to be 1 divided by a to the n. Okay. You see, here it is. Here's what I mean by the reciprocal. If you have a divided by b to the negative n power, then you do the reciprocal and it becomes positive, the exponent. That's really what we're applying here. The same concept. Number 7, the zero exponent property. Anything to the 0 power is equal to 1. And in this case, a to the 0 power is 1. And again, a cannot be 0. This is called a fractional exponent. If you have a, which is a base, to the power of m divided by n, the n is called the index, and then the a is called a radical, and the m is the exponent. So a to the m, a to the power of m divided by n, this is how you go from exponential to a radical. And these two are the same, these two properties here, but you can write them in 2 different ways. Now, n has to be more than 2, because if it's 1, then the answer will always be 1. Now, let me show you examples of each one. Okay, remember, this is the product rule. If you have a to the m times a to the n equals to a to the m plus n. Again, a is the base and m is the exponent. Must have the same base to apply the rule, right? The bases must be the same. Example, x to the third times x squared is equal to, here guys, I did it like the long way so you guys can see exactly what's taking place. For example, the one in blue, right, x to the third power is in blue, so I put 3 x's because x to the third is x times x times x. And x squared in green, x squared will just be x times x. So how many x's do we have? 5, right? So it's going to be x times x times x 5 times will be x to the 5th power, But if you apply the rule, right, by the rule, you have the same base, then you add the exponents, 3 plus 2. This is what's taking place, but it's better to use the rule. You have x to the 7th times x to the 3rd power, right? So we have the same base, so we're going to add the exponent, which would be x to the 10th power. X squared times y to the 4th power, these are not the same base. So you leave them how they are. You cannot simplify them because they have to be the same base. Now look at this one here. Here you have parentheses, 5x to the 4th power, close parentheses, times negative 3x squared, close parentheses. So here, guys, we're going to multiply the coefficients. For example, 5 times negative 3, and then we're going to have x to the 4 plus 2 because they're the same base, so you add the exponents. So the answer will be negative 15, x to the 6th power. Okay, this one, I guess if you want, you can get the answer without showing this step in the middle. For example, what's negative 2 times negative 3 will give us a 6. And then here, x to the 4th and x to the 5th, right? They have the same base. We're going to add the exponents. Also with the y's, they have the same base. So we're going to add also the exponents for the y. So this is the answer, negative 2 times negative 3. X to the 4 plus 5 and y to the 3 plus 2 will give us 6 x to the 9th, y to the 5th power. Okay, and this one I just did, I didn't show the middle step. You see negative 5 times 6 is negative 30. You have an x to the 1st power and x to the 3rd power. You add the powers. 1 plus 3 is 4. Since the 6x cubed doesn't have a y, we'll just bring the y cube over. So this is your result. Now this one, right, we're going to have 3 times 3 is 24. 3 times 8 is 24. X to the 4th times x to the 5th is x to the 9th. And next, y cubed times y will be y to the 4th. There's your answer, 24, x to the 9, y to the 4th. Let me go back again. So again, guys, like I repeat, you can go straight to the answer, right? Without showing the middle part. But if this is confuse you, keep doing the second step here. For example, when you're gonna multiply the coefficients and then put the x to the 4th plus 5 and y to the 3rd plus 1, you can do that step if this confuses you. Okay, but I believe this is straightforward. Okay. Now, rule number 2 is called the quotient rule. Okay, when you have the same base, but you're dividing a to the m divided by a to the n, you subtract the exponents. It'll be a to the m minus n. Example, same base, x to the 5 minus 2 will give us x to the 3rd power. X to the 10th divided by x to the 7th will give us x to the 3rd power because it will be 10 minus 7 will be 3, x to the 3rd power. X to the 4th divided by x to the 8th, the answer should be x to the negative 4, right? Because 4 minus 8 is negative 4. Now, I believe in rule number 6, we're going to deal with exponents. So for now, we just have that as the answer. But this can be simplified to something else, okay? Which is a negative exponent, which will be rule number 6. I'll show you that example when we get there. Rule number 3 is called the power rule. If you have a base power raised to another power, you multiply the powers. So x cubed, parentheses x cubed, close parentheses squared, will give us x to the 3 times 2, will give us 6, right? Or you can do it this way, right? You can expand it. It will be x cubed times x cubed will give us x times x times x, right? 6 times will give us x to the 6. So eventually, this x cubed squared is the same thing as x cubed times x cubed. And then if you expand them, it will be x times x times x times x times x times x 6 times, right? Or you can go from here to the answer. But here, I'm just showing you that there's different ways to get the same answer. Okay, but we're going to be applying the rules, right? X cubed to the power of 2 will give us x to the 6th power. Negative x to the 4th power. Here, guys, the answer is going to be positive, right? Because Check this out. Negative x to the fourth squared will give us negative x to the fourth power times negative x to the fourth power, right? Negative and a negative will give us a positive, and 4 plus 4 is 8. Remember that any negative to the even power is going to be positive, and any negative to the odd power is going to be negative. Okay. For example, this one here. We have parentheses negative y squared close parentheses. Remember what I just said? If you have a negative raised to an odd power, the answer is going to be negative. So this is going to give us negative y to the sixth power. How? Right, here it is. So we're going to do it 3 times. So it will be negative y squared times negative y squared times negative y squared. Negative y squared times negative y squared will give us y to the fourth, right? But we need one more because there's 3. So you see now this will give us a negative, and then we add the exponents. It's very helpful just to use the rules. Okay, now the power of a product rule and power of a quotient rule. This is rule number 4. If you have parentheses a times b to the nth power equals to a to the nth and b to the nth power. Example, this will give us x squared times y squared. This here is going to give us 2 to the third power times x cubed will give us 8x to the third power. This will give us what? X to the 6th, y to the 8th. Right, because we multiply the power, we distribute the power there. Like 3 times 2 is 6, 4 times 2 is 8. Okay, how about this one here? Remember that we have a negative, right? To the odd power, the answer is going to be negative, okay? But let's see how we do this one. Negative 3 to the third power is going to give us negative 27. X squared to the third power will give us x to the 6 because we multiply the powers. And y to the first power to the third power will give us 3. Here's how. Okay, again, I'm going to do it 3 times, right? Because it's cubed. Negative 3 times negative 3 times negative 3 will give us negative 27. X squared times x squared times x squared, right? We add the powers. 2 plus 2 plus 2 will be 6. And y times y times y, right? We add the powers. There's like a 1 there. 1, 1, and 1 will give us 3. Okay. Or negative 3 to the 1 times 3 power. X squared, right? X squared. So we distribute the 3, right? So it'll be x to the 2 times 3 and y to the 1 times 3. It will give us negative 27, x to the 6, y to the third. At times, when students will ask me, Mr. Isashi, so how do you do it? So I always give them different options because we all think different. So it's up to the student how he or she wants to pursue how to simplify these type of rules for exponential properties. Now comes the power of a quotient rule. Okay, so the power, right, again is going to be x divided by y to the third power is going to be x cubed and y cubed divided by y cubed. This will give us what? X to the 10th power because we multiply the powers over x to the 15th power. W to the 15th power. This is your result. Hey students, if you have any questions as I go along, please write in the chat, and the moderators will let me know there's a question, so that way I can explain it. Okay, don't hesitate to ask. Examples. These are negative exponent rules and zero exponential rule. If you have a to the negative n, it's going to be 1 over a to the nth power, and a cannot be 0. Example. X to the negative 5th power will give us, it's going to be 1 over x to the 5th power. That's how you apply the rule. 3 to a negative second power is going to be 1 over 3 squared, which will give us 1 over 9. Number 22. Parentheses x divided by y to the negative 3rd power. Right? Remember what I said earlier, that we use the reciprocal and you make it positive. So this is your result. Y cubed divided by x cubed. Okay, now let me show you how it's done. Remember, because right, if you have a negative, right, you make it positive by sending it to the bottom. So this is by applying this rule here. Now, 1, right, when you're dividing, this becomes multiplication, right? The division becomes multiplication, and you do the reciprocal on the second fraction, right? Now you multiply, so it's going to give us parentheses y divided by x to the third power. Here's how you apply the rule. But it's easier to just use a reciprocal, okay? From the beginning. If you have a fraction to a negative power, all you do is flip the fraction and make the exponent positive. Okay. Example, let's apply the rule here, right? Reciprocal, make it positive, distribute, so it'll be 5 squared divided by 2 to the second power will give us 25/4. That's our solution. Now comes the rule number 7, the zero exponent rule, which means a to the 0 power will give us 1. X to the 0 power, the answer is 1. Parentheses 5xyz to the 0 power, the answer is 1. Remember, anything to the 0 power is 1. Now comes the fractional exponent rule. Okay, this is rule number 8. If you have a to the power of m divided by n, the n becomes your index, right? And the a goes inside the radical, and the m is the exponent. Okay, n is the index, a is the radicand or the base, and m is the exponent, which was a numerator from the exponential fraction. That's a radical symbol. Okay, so it's always good to know, right? Now, what's x to the 1/3 power, right? Remember, 3 will be the index. X is going to be the the radicand, and 1, right? It'll be x to the first power. Okay, now how about 27? X to the power of 3 divided by 5. Remember, 5 is my index, right? So 5 will be the 5th root of x to the 3rd power. Hey guys, at times I'm surprised the students taking Cal, because you have to know this also for Cal 1. Cal 1 and some other calculus courses, and some students they don't know how to do converting from exponential to radical, and to me that really surprises me. But anyway, here's how the rules apply. For example, this one here, right? If you notice the 3w is in parentheses, so that means the 3w is going to be my radicand. That goes inside the radical. So this is the index, which is the denominator, and the power is 2. So this becomes, this you could simplify it further. This could have been the cube root of 9w squared, right? But that's okay, we leave it like that. Now in this one, we have to go the other way, right? This is going to give us the radical, and we have to put it as an exponential. There's my a, which is that, and my n is my 7, and my m is a 2, which is the exponent. So it'll be 8xy to the power of 2 divided by 7. Again, 6, it'll be 6x to the 1/4 power. Here, guys, this is a common mistake the students make. They say that it's 6x to the 1/4 power. This is wrong, okay? Because the whole 6x has to be in parentheses, because the whole 6x is a radicand. So this is a common mistake that students make. They don't put it in parentheses. Okay? Please be careful. Right? This is equivalent to this right here. You see, because the base here, the x to the 1/4 power, only the x will be the radicand. You see, the 6 has nothing to do with the 1/4. That's why these two are not the same. You see? That's why, please be careful. Okay, now simplifying radicals. Okay. Need to know basic roots such as square roots, cube roots, and fourth roots. These are perfect squares. Like the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, right, and so forth. Try to know as many as you can, maybe all the way to 10. Right? That'll be 10 right there. Now cube roots. Know at least up to 5. The cube root of 1 is 1. The cube root of 8 is 2. Why is this true? Because 2 times 2 times 2, 3 times will give us 8. Okay? At least know up to 5. For the false roots, at least know up to 3. Okay? Now, these are perfect squares, perfect cubes, and perfect fourth powers. Here we go. Example of simplifying a radical. Here they give the square 24. The square 24 is not here, right? It's not here because the square 24 is not a perfect square. So you have to find the factors of 24, right? No, it's not a perfect square. So we need to find the factors of 24. You have to find all the factors, right? Then from here, from the list of factors, which one is the highest perfect square? The answer is 4, right? Because 1 is a perfect square, right? But 1 doesn't count because it's the lowest. 24 is not a perfect square, nor the 2, nor the 12, nor 3, nor the 8. The 4 is a perfect square. So that's why this is a combination that I'm going to use. Okay. Now you can separate them. What's the square root of 4? The square root of 4 is 2. So it'll be 2 square root of 6. That's your solution. That's how you simplify radicals. Okay. This is your answer. Now comes everything that I just showed you is to assist you, well, also with 1324, but mostly is to help you with the NCBN 0324. Now all this from this present slide forward, all this is material from 2412, 1324. Okay, these are examples of exponential functions. Okay, if you notice, we have an exponent as a variable, as the x. Right? Everything with the exponent of x are called exponential functions. These are all examples. Okay. Now recall the base, right, to the power of m over n, right, is equal, right, is the same thing as a to the f of x, right? This is an exponential function right here. This will be similar to this right here. Okay. Now, a is the base, right? The exponent is a variable letter. The exponent is always like a letter. Most of the times it's x. You see, but in this case, it was m over n. It can be also, an exponent. Here we go. Okay, so how do we graph this? We're going to show you how to simplify it and also how to graph it. Okay, for now, say they give us f of x equals 2 to the x power. So they want you to find find y when x is negative 2, negative 1, 0, 1, 2, and 3. So let's do ourselves a little table. Right, we're going to put all the values for x. So when x is negative 2, what's y? So I'm going to plug in negative 2 where the x is, right? So 2 to a negative 2, right? Then we apply the rules. It will be 1 over 2 squared. The answer will be 1/4. So when x is negative 2, y is equal to 1/4. Now when x is negative 1, right, we repeat the process, but now instead of negative 2, we're going to plug in negative 1 for the x. So 2 to a negative 1 is equal to 1 over 2 to the first power. The answer will be 1/2. So when x is negative 1, y is positive 1/2. Now let's write 0, f of 0. F of 0 means that I'm going to plug in 0 for the x's, right? So remember the 0 property? Anything to a 0 power, the answer is 1. Common mistakes that students make, they at times say that it's 0, which is a common mistake that they make. So just remember that anything to the 0 power, the answer will be 1. Okay, now let's see here. Now, so when x is 0, y is 1. Now let's see when x is 1. When x is 1, right, 2 to the first power will give us 2. Now when x is 2, right, we evaluate at 2, so 2 squared will give us 4. And when x is 3, It'll be 2 cubed will give us 8. So these are the results. Okay, when I mean, for this problem, they actually gave you the values for x. But when you be graphing these type of problems, they're not going to give you the table. But most of the times, these are the numbers that you use for x. Okay, and there's your graph. For example, when x is -2, right? -2, this will be about 1/4 right there. When x is -1, it's going to be about 1/2. When x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. And when x is 3, y is 8. I tell my students also to be wise. For example, if you want to use 4, right? Say you want to use 4, it's going to give you 16. You see, most of the times it's going to be out of the grid. So that's why be smart with the numbers that you use. But most of the times you're going to be choosing numbers like from -2 all the way to 2 or 3. Okay, it's rare when you use all the way to the fourth power. When x is 4, because 2 to the fourth power will give us 16, and like I said, it'll be out of the grid. Okay, now exponential functions graphs. Okay, this graph is going to be exponential growth. Okay. These are the characters. The graph is above the x-axis, right? This is the x-axis. The y-intercept is 1. The graph climbs steeply to the right, right? It goes steeply to the right. The negative x-axis is a horizontal asymptote, right? This right here, guys, from the negative x-axis is a horizontal asymptote because it means that the graph will never reach the negative x-axis. The larger the base, the more steeply the graph rises to the right. For example, if A is 2, right? Say that's probably be the graph, something like this. But if A is 4 or 5, the graph begins to get steeper. Okay, it goes closer to the y-axis, the bigger the base. You see, here's an example. This is the one in green is like the basic graph, right? Y to the y equals 2 to the x. The base is 2, right? You see, it'll be something like this in green. The bigger the base, right? Now it's 3. You see, it goes more towards the y-axis. Y to the 10th, right? 10 to the x power, it'll be, it's getting closer and closer to the y-axis. And if it's less than 2, right? Say this is like 3/2, 1.5. You see, the smaller the base is, the more it goes towards the x-axis, to the positive x-axis. Okay, now this is decay when a is between 0 and 1. When a is between 0 and 1, the graph is above the x-axis. The y-intercept is also 1, but the graph falls sharply to the right. Right, the graph starts high and it goes down towards the x-axis. Never reach the x-axis. It'll get closer and closer to the x-axis, but it will never reach it. The positive x-axis is a horizontal asymptote, right? This is the asymptote, the positive x-axis. The smaller the base A, the more steeply the graph falls to the right. Okay, now, and there is a graph. You see 1/10, 1/10 to the x power in blue, 1/3 to the x power in red, 1/2 to the x power, and 2/3 to the x power. Okay. Again, the higher the higher the number, the more it falls towards the left. Let's see here. Okay, now let's graph this one here. Right, first we apply the rule. This is the same thing as 1/2 to the x power. So to graph it right, we're going to choose the powers, right, for the x. And again, we always choose like -3 all the way to 3 or -2 all the way to 3. But these numbers should always be -3 or -2, -1, 0, 1, 2, and 3. Now, if we plug in -3, right, it's going to give us 8. Why is that? When we plug in -3 for the x, Right? Remember, if it's negative, right, exponent, right, and it's a fraction, we do the reciprocal and make it positive. So the answer is 8. Okay. Now, if we repeat the process for all the values, this is what we get. Because when x is negative 2, right, we do the same the same type of evaluation here. It's going to be 1/2 to a negative 2 power, right? We flip, we use a reciprocal. We use a reciprocal, right, and then we make it positive. So anyway, this is the graph here for the decay, or it's called decay. The one that goes starts low and goes up is the growth, and the one that starts high and goes down is decay. So anyway, this is a graph. This is how you graph these type of functions. Now these are called logarithms. Okay, to the development of computers and calculators, logarithms were the only effective tool for a large-scale numerical computation, no longer needed for this purpose because we have calculators now. For example, the definition of logarithms to the common base 10. If you have y equals to log base 10 to the x, is the same thing as y equals to log of x, right? If there's no base, it means it's base 10. And this means 10 to the y power equals x. So right now I'm going to show you how to convert or how to rewrite logarithms to exponential and exponential functions to logarithmic functions. This is the purpose of this presentation here. Again, right, no base is the same thing as means base 10. Okay, simplified without a calculator. This is how you read it. To what exponent must 10 be raised to get x, right? So the answer will just be, the answer there will just be 1. Let's look at this one here, right? So the base is 10. So 10 to what power gives me 100? The answer is 2, right? Because 10 squared will give us 100. Log, right, this is base 10 again because there's no base. We have 10,000. So 10 to the what power will give me 10,000? The answer is 4. Because 10 to the fourth power will give me 10,000. Log base 7 to 49, right? This means 7 to what power will give me 49? The answer is 2. Log base 3 27. This means 3 to what power will give me 27? The answer is 3. But not every time. But every time it's going to be like a perfect log. At times, that's why only at times you're going to be using. Let me go back a little bit. At times this can be done with a calculator, but for now they want you to do it. To do it without, just to show you the meaning. Behind it. But most of the times students use a calculator, and most of the times the calculators do not have any other base besides base 10. So if it's like another base, the calculator will, more likely will not be able to conduct the evaluation of whatever you're trying to find. But there's a way, right, which is called the change of base, which I believe I'm going to show you later on this PowerPoint. For now, they want you to write exponential equations and to logarithmic equations and vice versa. Here's the definition of logarithms to base a. If you have y equals to log of base a, x means a to the y equals x. This is logarithmic. This is exponential. Okay, example, write each logarithmic equation into an exponential equation. Here's where I tell my students what to do. Okay, you want to go from logarithmic to exponential. So from the log that was given, the log equation, you have to know what the a is, what the x is, and what the y is. If you notice, my a is 9. My x is 81. And my y is 2. Right? So now it's going to be a to the y is going to be 9 squared equals 81. There's my a, the 9. There's my y, the 2. And there's my x. That's how you rewrite it. Okay. For example, this one, right? Again, we have to find my a, my x, and my y. Here they're going the other way. They're going from exponential to logarithmic. Okay, so my a is 5, my y is 3, and my x is 125. So it's going to be y is 3, so it's going to be 3 equals to log of 5 at 125. Again, there's my y. My y is 3, my a is 5, and my x is 125. That's how you go back and forth. Okay, I believe this is the only examples that I'm going to do because this is so basic. Just by knowing what the a, the x, and the y are, you'll be able to convert it or to rewrite it from logarithmic to exponential or exponential to logarithmic equation. Now, this is the logarithmic functions that you need to know how to graph, okay, without a calculator. So remember, guys, we're going to use this rule, right? We have to go from logarithmic to exponential in order to graph it. Example, we have y equals to log of base 2x, right? So by applying the rule, right, or the conversion, it's going to be 2 to the y equals x. So we're going to graph 2 to the y equals x. But check this out. Instead of plugging in the values for x, we're going to plug them in for y. Okay, why? Because y is the exponent. And these are the values that we get, right? By using the same rules that we applied earlier. For example, if we have y to a negative 2, right, it's going to be 1 over 2 to the second power will give us 1/4. So again, we apply the same rules as what we did in the last PowerPoint. I mean, in the previous 2 or 3 slides ago, where we were graphing the exponential function. I believe it was 2 to the x. F of x equals 2 to the x power. This is y equals to 2 to the x, the one that we graphed earlier. And this is a logarithmic. If you notice, these are inverse of each other. Okay, but I believe for 1324, we don't really cover that. But for 1314, they do. Okay, but this is where we graph the logarithmic function. The logarithmic function will always go like this, guys. This will always be the logarithmic function. This is a characteristic of the logarithmic function. And for the exponential, it's going to be the one in blue. So almost every exponential will be in this format. And every logarithmic graph will be in the format in the red function here, in the red graph. Okay, now this is how you apply it in a real life format. For example, it says the assets in billions of dollars for a Prudential Financial Incorporated can be approximated by the function a of x equals to 315 e to the power of 0.056 x, where x equals 7 corresponds to the year 2007. Find the assets for the following years, for the year 2000. So solution is, since x equals 7 corresponds to 2007, then x equals 0 must correspond to the year 2000. And x equals 12 corresponds to the year 2012. So eventually, we're going to be evaluating the function at x equals 0 and x equals 12. So we're going to find a of 0. All right, we're going to plug in 0 for the x. So the answer will be 0.056 times 0 will give us 0. E to the 0 will give us 1. 315 times 1 will give us 315. But it's in billions of dollars, so it'll be $315 billion. Now for B part, right? But anyway, this is something extra. Good to know that every time that x is 0 or t is 0, that's my initial value, 315. It's good to know for the next problem that I'm going to explain to you guys. But before we do that one, let's do B. We're going to evaluate a to the 12th. Right, we're going to plug in 12 for the x. So then we put it there in the calculator, and it's going to give us 616.8171575. Remember, it was in billions of dollars, so it's going to be something like $606.8 billion. That's the answer. And again, I put here in red. Make sure that if your calculator doesn't give you the exponent, right, like that you can see it on the screen, then you have to put parentheses. So you have to be careful with that because most of the times, a common mistake that students make, they just put 315e to the 0. To the 0 to the 0.056 times 12 without the parentheses. So that's going to give them a wrong result because what it does, the calculator will follow PEMDAS. So what it would do, it will first multiply 315e to the 0.56, right? And give you the answer and then multiply that by 12, which is incorrect. In this case, be wise and be careful how you put the parentheses. Okay. Okay, now this is a problem that I came up with the time of during COVID. During COVID, I believe this was before spring break because we went into online after spring break when COVID struck here all over the world in 2020, right? So I use this example to show my students how can be applied like in a real life situation, something that we can relate to. Okay, here's a problem here. A deadly virus has affected the world. At the end of January, there were 2 cases, and by the end of April, the cases had grown to 128. I believe I got this info, guys, because I believe at the end of January there were 2 cases. I believe in Washington. So Washington State. I believe something like that. And then by April there was 128. Okay, so this is like a real life scenario. Now for A, they want you to find a model of the form f of t equals to y naught b to the t power with t equals 0 corresponding to the end of the month of January. And then B, if the trend continues, about how many people will be affected by the end of the year. Okay, so let's tackle this problem here. So I need to find y naught. Hey guys, y naught is the initial value, and B, right? And B, we need to find these 2 variables in order to come up with a function or with a model. So y naught is the amount present at time equals 0. Since t equals 0 corresponds to the end of January, right? This is here, deadly virus at the end of January, right? So we had 2 cases, so it'll be 0, 2. Y equals 2, right? So, and then I went like this, t equals 1, right? Because by the end of, of April, the cases had grown to 128. So t equals 1 corresponds to the end of February, t equals 2 corresponds to the end of March, and t equals 3 corresponds to the end of April, right? So this is what we need here. So then we have to find 2 points, right? So we got, these 2 in between, guys, I didn't need to put them there. I just did them, guys, so you guys can actually have a visual, okay? But you can account it with your fingers, right? February will be 1, March will be 2, and April will be 3. So with that said and done, right? So we have 2 points. We have my initial value will be 2, right? Y naught will be 2. Why? Because remember, when t equals 0, that's your initial value. So y naught is 2. Now I need to find B. The B, I'm going to find it with 3, right? It was the end of April. There were 128 cases. So f of 3 equals to 128. So 128, right? So I'm going to plug in the formula, right? So f of t equals to y naught b to the t power. So f of 3, which is 128, equals to the y naught, which is 2, b to the 3rd power. So I need to solve for b. So I'm going to divide both sides by 2. It's going to give us 64 equals b cubed. Now I'm going to raise it to the power of 1/3. Right, this right because now we apply the power rule, right? An exponent to another exponent, we multiply the exponents, which will give us 1. That will give us b by itself, and 64 to the 1/3 power. You can use the going from exponential to a radical, right? Or you can put it in the calculator. So the answer is 4. So b equals 4. Y naught equals 2, and b is 4. So let's plug them into the formula. There's my y naught is 2, and my b is 4. So this is my model or the function that we're looking for. Okay. So that's the answer for A. But for B part, it says, let me see here, if the trend continues about how many people will be infected by the end of the year. So from January to December is 11 months. That's why we're going to evaluate f of 11, which means I'm going to plug in 11 where the exponent is, where the t was, right? So this will be the result, guys. about what is it, 8,388,680 people will be infected by the end of the year. That was the case, right? But this wasn't the case because there were interventions. For example, there was social distances. There were also what else was there? There were also the vaccines came up. They came out with the vaccines, but this will be effective or accurate if there was no interventions. If it just played out how, with no medical attention or with nothing like that, this will be like a good estimate to, I mean, for that many people to be infected at the end of the year. And I guess I believe this is a PowerPoint of my presentation. I want to thank you for your patience, and I hope this was useful, and I want to thank you again. Let me stop sharing.
Okay, thank you, Mr. Isasi, for your wonderful presentation. We do want to remind you all about our previously recorded sessions, which are available also on a YouTube playlist. This session will also be available on that list later today. Also linked is a short survey to help us improve our TV sessions. Please take a few minutes to fill out that survey. Before you leave, I want to share the TV sessions that we'll have next. Okay, at 1 p.m. today, we have the fall 2023 student handbook. We will be back with happy hour, math hour next week at 11 a.m. And in math 1314, we will cover synthetic division and complex numbers. And math 1324 will cover solving exponential and logarithmic equations. Our 1 p.m. session next week will be mental health and anxiety by the EPCC Mental Health Committee. Thank you all for coming in today. We hope you all have a lovely weekend. If you have any questions, please feel free to use the chat box or your mic, and we hope to see you everyone again for Happy Math Hour.